Exponential functions. An exponential function can always be written in the form of a times b to a power. Your power here is your x. Whenever your exponent is your variable and it's equal to y, then it becomes an exponential function. So here we have two more exponential functions. One of them is in the form of y equals a 1 times a 2 to the x. In this case, when you look back up here, your a is your 1, your b is your 2, your exponent is still the x. Here, it's in the form of y equals 1 times a 1/2 to the x. We want to go ahead and make a t-chart for each one of these and graph our functions. So if you've not done so, complete your t-chart. Plot your points and draw in a smooth graph connecting all of them. And do the same thing for your 1/2 to the x. What we have here are the graphs of two exponential functions. These are the two main types of exponential functions. Your red graph goes up as you go to the right, so it's referred to as a growth graph. Your blue graph goes down as you go to the right, so it's referred to as a decay graph. But for the most part, each graph is the same shape. You'll notice the blue graph is just the reflection of the red graph over the y-axis. That's the basic shape of any exponential function. So, whenever you're having a growth graph, your b, what your exponent is on, is greater than 1. And that's what we had here for this one here. What your exponent is on was a 2. So that's why the original one was the growth graph. Here, what your exponent is on is a 1/2. Whenever that b value is between 0 and 1, we end up getting a decay graph. In each case here, when we were looking at our problem before, our y-intercept was 0. But that's because they're all in the form of y equaling a 1 times something to the x power. So your y-intercept was 1. When you go ahead and plug in 0 here, you get b to the 0, which is 1. 1 times a is a. So when you plug in 0, you get a. So your y-intercept is a. When you look back at your graphs there, where did they cross the x-axis? They did not cross the x-axis, so you had no x-intercepts. You did have a horizontal asymptote. Each graph did level out at a height of 0. Our original problems we were just dealing with were always in the form of a times b to the x. Since we were not adding anything here, we are really technically having a plus 0. So that ended up being your horizontal asymptote. If you chose to have a number here, it would then move your whole graph up, including your horizontal asymptote, or it would move your whole graph down, including your horizontal asymptote. So if you have plus a number, it changes your horizontal asymptote. So let's go ahead and solve this. Since we have 6 to a power on the left, 6 to a power on the right, we can go ahead and drop the bases of 6 and just set your exponents equal. Then we're going to go ahead and just solve it for x by adding an x, subtracting your 1, and dividing, and we get our power, or x being 2. And you'll notice if you plug it back in, you would get an exponent of 5. Plug it in over here, you get an exponent of 5. So you get the same power on each side. So basically, whenever you have the same base on each side and they're equal, you can drop your bases. So here we don't have the same base, but we could go ahead and rewrite each side so they're the same base. We could think of 27 as being a 3 cubed, still raised to the x minus 1. You could think of your 9 as being a 3 squared. So then you're going to go ahead and have the same base on each side. But prior to dropping your bases, you want to get rid of your parentheses. Here we have an exponent raised to an exponent. So you want to make sure you multiply your parentheses. Same thing on the right. You have an exponent or a 3 raised to a power, 3 raised to a power, the same base on each side, so you can drop your bases and just work with your exponents. When you solve it, you'll end up getting 3. Just as a quick review, remember if you have an x minus 3, it moves your graph 3 units to the right. If you have minus 3 after you do your squaring, it moves it 3 units down. That same type of translation, moving your graph vertically and horizontally, also works with exponential functions. Let's go ahead and start out with a 2/5 to the x power. Go ahead and complete your t-chart and then plot your points. Completing your t-chart, we end up getting this. Plotting your points, connecting all your points, we get a nice smooth graph like this here. Once again, we would have arrows going in each direction here. It goes on forever as you go to the right, goes up here. Well, when we take this original function right here of our 2/5 to the x, and then we go 2/5 to the x with a minus 3 next to your x, you should realize that all that does is just move your graph 3 units to the right. So you're going to take your original graph you just had, move it 3 units to the right, and draw in your graph. Or here, we're subtracting 3 after we do our function. So all that's going to do is take your original graph and just move it 3 units down. So you take your original points, move everything 3 units down, draw in your graph.